Okay. So the system that we are looking at is defined, or the output or the input-output relationship for the system that we are interested in is given by y of t is x of t minus 2 plus x of 2 minus t. Okay. And the question is whether this system is linear, time invariant, memoryless, causal, and stable. So let's start with determining if the system is linear or not. So what's your intuition? Anybody thinks this is not linear? Okay, so we have some doubters, so we'll work through the problem to see whether it's linear or not. So to see whether a system is linear or not, what we have to do is this. So we have to consider three inputs to the system, right? So first, let's consider an input x1 of t to the system, and let's assume that the output from the system is y1 of t. But the input-output relationship for the system tells you that y1 of t is nothing but x1 of t minus 2 plus x1 of 2 minus t. Does that make sense? Okay. Then we think of another input. Let's call it x2 of t. And let the output of the system for this input be y2 of t, which is given by x2 of t minus 2 plus x2 of 2 minus t. All right. Now what do we have to do next? I want to determine if the system is linear or not. So if the system were to be linear, the output of the system corresponding to a third input, which let's call it as x3 of t, given by a times x1 of t plus b times x2 of t. I want to look at the output of the system for this input, and I want to see whether that is the same as a times y1 of t plus b times y2 of t. If that turns out to be the same, then the system is linear, otherwise it's not. That makes sense? So let the output of the system for this input be y3 of t. And what do we know about y3 of t? Well, what we know is that y3 of t is x3 of t minus 2 plus x3 of 2 minus t. But writing it like this does not help us immediately, and what we would like to do is to have everything in terms of x1s and x2s so that we can see whether y3 of t is equal to a times y1 plus b times y2. So I'm going to try to replace x3 of t minus 2 and x3 of 2 minus t in terms of x1 and x2. So what do I know about x3 of t minus 2? Well, I can get x3 of t minus 2 by replacing t by t minus 2 in this expression. So that tells me that this is a times x1 of t minus 2 plus, what do I get? B times x2 of t minus 2. Does this make sense? I've just written the first part. This is just x3 of t minus 2. Okay. Now we need to write a similar expression for x3 of 2 minus t. And what is x3 of 2 minus t? That's obtained by simply replacing t by 2 minus t in this expression. So this must be a times x1 of 2 minus t plus b times x2 of 2 minus t. Alright. So the question now is whether y3 of t given by this expression is the same as a times y1 of t plus b times y2 of t. And indeed, if we just write a times y1 of t, we're going to get a times x1 of t minus 2 plus a times x1 of 2 minus t plus b times y2 of 2 is b times x2 of t minus 2 plus b times x2 of 2 minus t. Does that make sense? Now, of course, we can see that these two are indeed the same. And what's really going on here, and the reason the system becomes linear, is because addition is associative. Now, what I mean by that is I could move this a here and then think of it as a times x1 of t minus 2 plus a times x1 of 2 minus t. Right? And then I can pair the two x2's together and you can see you get exactly a times y1 of t plus b times y2 of t. So the system is in fact linear. So any questions so far? No? Okay. So now let's talk about whether this system is time invariant or not. So the test to see whether this is time invariant or not is going to be to do two things. First, take x of t, shift it by t naught, and think of a signal x1 of t, which is the result of shifting x by t naught, and then pass this through the system, and let's say the output signal is y1 of t. And then what we do is we take x of t, pass it through the system first, let's say the output is y of t, and then we shift this by t naught to get y2 of t, and we ask ourselves, is y1 of t the same as y2 of t? If it is, then we say it's time invariant. Okay. Now all that remains is to write the expressions for all these signals, and that's where things can get a little bit tricky in one or two places. So let's carefully do this. So what's the expression for x1 of t? Now x1 of t is simply x of t minus t naught, right? It's simply a shift of x by t naught. You with me so far? Okay. Now we're going to pass the signal through the system to get y1 of t. What is y1 of t? Now y1 of t is x1 of t minus 2 plus x1 of 2 minus t. Right? That is the input-output relationship for the system. But what I would like to do is to not have the x1 there. I would just like to write it in terms of the x's. So in terms of x's, what is x1 of t minus 2? Now this is the important part that I want you to pay attention. So to find that out, so what are we really doing here? So we have an expression for x1 of t in terms of x of t. So x1 of t minus 2 means simply replace t by t minus 2 in this expression. Right? That's what x1 of t minus 2 is. So x1 of t minus 2 must be x of t minus 2 minus t naught. Alright, now for the x1 of 2 minus t. Now what is x1 of 2 minus t? Well, that's what you get by replacing t by 2 minus t in this expression. Right? So this is x of 2 minus t naught. If you got this, then I think you are understanding what's really going on with this. Okay? Now let's work out the other part. So what is y of t? Yeah.
If you're replacing t with t minus t naught, shouldn't it be 2 minus t plus t naught?
Yeah, actually it looks like I made a small mistake when I said replace t by t minus t naught. It should be replace t by 2 minus t. Alright, for the second part, we take x of t, pass it through the system, we get y of t, and y of t is given by x of t minus 2 plus x of 2 minus t. Okay, now we are going to delay this signal by t naught. So y2 of t is given by y of t minus t naught. What is y of t minus t naught in terms of x of t's? Well, to see this, what we need to do is we take the expression for y of t and replace t by t minus t naught in the expression, right? So we take this expression, replace t by t minus t naught. So here it's replacing by t minus t naught. It's not replacing by t minus 2 or 2 minus t, because we are shifting that signal by t naught. And this is going to be x of t minus t naught minus 2 plus x of 2 minus t minus t naught. Now the first part you can see is the same as this. These two are the same. But the second part is not. Because if I were to write this, I get 2 minus t plus t naught. So these two are not the same. So clearly the system is not time invariant. Okay. In fact, what I would suggest, whenever you are asked to solve problems like this, if you have time, even just try a few examples. Try using some signals as inputs to get some intuition about what the system is doing. And this will actually help you a lot to understand what the system is doing. Now, you can never prove whether it's time invariant or not just by looking at a few signals. But nevertheless, it can give you some intuition. But what you may be able to prove is that the system is not time invariant, even if you find one input signal and one shift such that shifting that input by some t naught does not result in just the corresponding output being shifted by the same t naught. Okay. So maybe let's get some intuition for that also. Let's try some simple signal and let's see what happens when we pass this signal through the system. one simple signal we can try is actually just the impulse function for the input. Okay. Let's think about why this system is not time invariant, or let's look for an example to show that the system is not time invariant. I mean, this is not the only input. You can consider many inputs. Suppose x of t is just the delta function. What is the output corresponding to this input? I'm going to get some y of t, right? What will be the output? So you can see that y of t is x of t minus 2 plus x of 2 minus t. Now what is x of t minus 2 when x of t is the delta function? It's just delta of t minus 2, which means this is a delta that occurs at time 2. And delta of 2 minus t, what is delta of 2 minus t? It's the delta function shifted to the left by 2, right, and then flipped. Actually, it's not the goal post. I'm sorry, it's not quite the goal post, because it's shifted to the left by 2 and then flipped, which means it lands up right on this delta again. So this just doubles the magnitude of the impulse. Okay, so this is the output y of t, and what are we going to try to do now to see whether the system is time invariant? We're going to shift it by something. Why don't you pick the shift? Just pick some number. 4, okay. So what is x of t minus 4? So x of t minus 4 is a delta function that occurs at 4. So we're going to send this through the system, and the question is, what are we going to get? So what we are going to get is the input shifted by the first part is going to be, take the input shifted by 2 to the right, right? So that's going to be an impulse 6. What does the second part say? Well, take the input shifted by 2 to the left and then flip it about the y-axis. So I take the input shifted by 2 to the left, that puts me somewhere here at 2, and then I have to flip this about the y-axis, in which case it ends up being here. And indeed you can verify this too, because if you look at the mathematically, what is the output signal? The output signal is delta of t minus 2 minus 4 plus delta of mathematically, what is this? We want to take x of t minus 4 and replace t by 2 minus t. So it's delta of 2 minus t minus 4. Right? So this function is so this is delta of t minus 6 plus delta of negative 2 minus t. So indeed, this is this part and this is this part. Delta of negative 2 minus t is the delta occurring at t equal to negative 2, because when I plug in t equal to negative 2, the argument goes to 0. So clearly the output y of t was not just a shift of the input by 4 units. I think what really is happening here is the 2 minus t is the culprit, right? The 2 minus t is really like a shift to the left followed by a flip. So when you flip things around before you shift, it's not just the same as shifting it by the same amount, because you're flipping things around the y-axis, right? This is what makes it not time invariant. In fact, the simpler example to see this could have been just the system y of t is x of 2 minus t, or even just x of negative t. These systems are all not time invariant. Now, of course, when you see, x of t minus 2 plus x of 2 minus t, these problems look more complicated, so it's a good idea to work out a couple of these things. Alright, does this system have memory or not? It has memory because you can see right away that the output depends on x of t minus 2. It depends on some x of t other than just, or it depends on the input for some value other than t. So x of t minus 2. So it does have memory. Is it causal? No, it's not causal, because if you think about, so why is it not causal? It does or it does not? You sure it does not? If it did not depend on future values, then it would be causal. Causal means it does not depend on future values, right? Only the past and the present value of the input can affect the output in a causal system. But is that the case here? That's not the case, because if you look at negative values of t, I mean, think about t being negative 1, then y of negative 1, for example, y of negative 1 depends on x through x of negative 3 plus x of 3, right? Now, if I only had this, then I could conclude the system is causal, but I have x of 3 as well, and x of 3 is a future value for y of negative 1. So it's not causal. Is it stable? Everybody agree it's stable? Yeah, indeed it's stable, because if you really think about what's happening in the system is just taking x, shifting it by 2, making another transformation on the signal, but only on the independent variable, and then adding the two values together. So it's really not possible for y to become unbounded unless x is unbounded. But if you want to write a clear proof, we can say something like this. The magnitude of y of t is clearly smaller than or equal to the magnitude of x of t minus 2, plus x of 2 minus t. Actually, you can say it's equal to here in this case. I don't know, why did I say less than or equal to? It's equal to, right? But this is less than or equal to the magnitude of x of t minus 2 plus the magnitude of x of 2 minus t. Do you agree? The magnitude of A plus B has got to be lesser than or equal to the magnitude of A plus the magnitude of B. When X is bounded, we know that each one of this is less than a bound, which we typically denote by M sub X. So the first term is less than M sub X, and the second term is also less than M sub X. So clearly the magnitude of y of t is less than or equal to 2 times M sub X. So clearly y of t is bounded. For every bounded input x of t, the output is also bounded, and so the system is stable. Any questions?